Okay. All right, I'm gonna start rolling my intro.
There you go. What's up, you scholars of enlightenment? We're going to have a chat with Professor Jason Steffen over at Las Vegas University about a very hectic week in science. He's just setting up his tech. How's it going, Jason?
Doing well. How are you?
Not too bad. Seems like Lhcb results got swept away yesterday, but there we go.
All right. So now I'm not seeing your face. Are you?
What do you need?
I see your bubble.
You see my bubble. You can't see my face. Why can you not see my face? Should be able to on Skype, I think. Why is it not letting you? Let me see if I can fix that for you. Audio, video settings, camera. Maybe if I do that. HD. Why is it not coming through? That's odd. Anycam, virtual camera. Is it because Skype doesn't like me using OBS at the same time, perhaps?
Are you using the OBS virtual camera?
Not at the moment. Should I be?
I don't know. I use it sometimes, but
I'm just using my normal one, but it's black for some reason, which I don't really understand. Showing up in OBS, fine. Is it killer for you? Would you rather have me up, or you?
I'd prefer it because I'm gonna also record and upload our discussion.
All right, let's see if I can fix it then. So maybe if I go to, sometimes I run it through this Manycam application, which sometimes lets me have two things at the same time. So maybe if I can add a camera in there. So it's whinging. I think it's whinging because OBS is open. And then maybe if I make OBS watching video, and then maybe if I make OBS do my YouTube game capture, video capture, device 5, do Manycam. No, it's whinging. Why are you whinging? I think it's just whinging because it doesn't like, I don't know why it's whinging. I think it's just whinging because it doesn't like OBS being open at the same time. I'm not sure what I can do to fix it.
Okay. Maybe I can just put a picture up in your place.
Stick a picture up of me. I think people have had enough of my mug talking about this the last 2 days. Or I can send you the video. So if you want to use it, it's not a problem.
Okay. Let me. So
you're always sending me the video, so I owe you one.
All right, that sounds good. Okay, so welcome everybody. Let me also get my stream going.
That's all right. It's always a little bit of tech at the start. It's all good.
All right, welcome everybody. Hope that things are going well for you. We're going to be talking about some amazing stuff that has been going on this week with the bad boy of science, the bubble of the bad boy of science.
Yeah, so like I said to you, it seems like it's been a very hectic week in science. We had the Lhcb results sort of, seems an age ago now. What, about a week and a half ago? And looked like there might be some breakdown in lepton universality, but it was only a 3 sigma. So, most particle physicists don't get out of bed for 3 sigma. And then yesterday we had the g-2 results at 4.2 sigma. So a little bit more powerful, suggesting another deviation from the standard model. So lots going on in the world of particle physics.
So let's split our time between the two.
Sure.
So that we can let's start with the Lhcb results, so that we can so I can get some better idea of what's going on with Lhcb.
Yeah.
So it's not the most famous of all of the detectors at the Large Hadron Collider. So
no, but this is my experiment, Jason. Come on.
I know, but sometimes obscurity is better, right?
All right. I'll take the backhanded compliment. We'll go with
that. Like I have I don't know. I'm from a town. When I was young, I was from a town that has like 1,000 people in it. So I take great pleasure in being from a place that that people don't hear about that much.
No, it's no. You're right. You're right. It's no Atlas. It's no CMS. It's not one of the Higgs finding experiments. It's one of the smaller, less well-known experiments on the ring at the LHC at CERN. That's right.
Yeah. So typically, when people look at the Large Hadron Collider, the things that you see most often, the images that are displayed most often of the detectors, are of the Atlas and CMS detectors, and so those are the big detectors. Lhcb is one of the 2 smaller detectors. What's the last one? Alice? Is that what it's called?
Alice, yeah. Alice is on the other side of the ring. So people who used to work on Alice, the poor guys, Atlas.
It's like an hour drive, isn't it?
Yeah, exactly. So Atlas is separate, sat right there on the CERN gate, basically. And then Alice is obviously across the other side of this 27-kilometer circumference ring. So they'd have to drive all the way across the diameter, worse than the diameter, because you can't obviously go as the crow flies. So the worst place to be was Alice, right across the ring. We were at I don't know, which point is it now? So it was set out in 8s, and I think we were at something like 0.3. So it wasn't too bad. We were sort of round, not quite 90 degrees round the circle. So it wasn't too bad. But you were working at Atlas was definitely the easiest one. You just wandered across the road from the office and you were there. And as I say, Alice, get in your car, because otherwise you're not getting there.
Yeah, no kidding. So, all right. So LHCb, what is the detector like, and how is the detector different from the Atlas and CMS detectors?
Yeah, so LHCb is essentially a detector that looks at beauty and charm quarks and the decays thereof, looking at things like matter, antimatter asymmetries. In terms of the setup, it's a little bit different from Atlas and CMS, which are kind of barrel detectors that sit around the beam pipe in a sort of cylindrical setup. And then obviously the particles smash together and the particles stream out into that cylinder. LHCb is set up more like a wedge. So we only get particle collisions firing in one way, very close to the beam angle.
So you're not, LHCb is not a head-on collision. It's a fixed target experiment.
No, it's on the ring. So it's still a collision
it's on the ring,
experiment.
okay.
But we essentially lose half of the collisions, because half of it goes away from the experiment. So you can imagine Atlas is wrapped around the beam pipe, so it picks up all of the collision stuff, whereas LHCb is like a sort of wedge, like a door wedge shape. So the particles come in and smash together, half of the collision stuff goes this way, half goes this way, and we only pick half of it up. So just for cost saving, really.
Oh, so now are you picking up stuff that's perpendicular to the beamline?
Well, we can pick up some stuff that's perpendicular to the beamline, but mostly stuff that's very close to the beamline.
Okay.
So very sort of highly scattered forward. One of the things it looks at very much is the decay of B quarks, or hadrons that contain B quarks. And this is what it was looking at last week, or the results that came out last week. So we're looking at the decays of B plus, and they were decaying to essentially kaons and either a pair of muons or a pair of electrons. And the standard model tells us that due to lepton universality, the decay rates to to different types of leptons, so pairs of electrons or pairs of muons, for B quarks should be the same. And what LHCb saw was that it seems like nature is favoring B quarks decaying to muons instead of electrons. And that's not something you would expect. You'd expect the rates to be the same, obviously, after you...
Now, are the rates the same because the B quark is so much heavier than the muon and the electron?
I guess so. So you'd have to correct for kinematic effects, right? Because there's more phase space for the decays to electrons, I guess, because the electrons are lower mass. So you have to do some corrections. But in terms of the forces involved, in terms of the mechanics involved in the interaction, they should be exactly the same, because you've got this coupling of a W to, an E plus E minus or a mu plus mu minus. So the rates of these decays, the number of them you see, should be the same.
Okay, so you have the B quarks coming in. Does that mean that in order to produce the B quarks... Now, here's a quick question.
Good.
Do people still call it beauty, or did they stop calling it beauty in the 1970s?
Do you know what? I think most people I know call it beauty because they find it a bit childish and stuff to call it bottom. But, a bottom can be beautiful, I guess. Well, definitely can. So, most people say beauty because it sounds more... People in the UK and at CERN have their minds in the gutter, and people because I've always learned at the bottom quark, because like top and bottom. Yeah, up, down, charm, strange, top and bottom makes... People would say it like that. I find most people say beauty. Maybe it's because it goes with the charm as well. So I can say, I studied charm and beauty at the Lhcb experiment. It sounds quite...
Okay. So, because I always was
grandiose.
Like... The way that I learned it was that they were going to call it beauty, but they got sick of strange and charm as these things, and they were like, okay, we're not... The 1970s are over, hippies are out, and now we're getting into new wave and rockers. As the In Excess is all the rage, and Tears for Fears, and so we're going to just call them bottom and top. So
I guess Large Hadron Collider beauty experiment sounds better than LHCb bottom experiment. Large Hadron Collider bottom experiment makes it sound like it's the worst, the lesser one. So maybe that's why they.
Interesting cultural note, because I had never heard it referred to seriously as the beauty quark until I guess today.
Yeah.
So
anyone who's listening can substitute beauty for bottom. In most contexts, and it's fine.
Now, does the LHC have to operate in a particular phase or in a particular mode for your experiment to operate, or do they just run it at whatever full?
No, so they just
power?
So they just run the beam as normal, and there's various points where the beams are brought into collision. So what they have, from my understanding of the operation of the machine itself, is you have obviously there's circulating beams of protons, one clockwise, one anti-clockwise, counterclockwise, and then at various points around the ring, these 8 points. So Atlas is at point 1, Alice is across the ring at another point, and at these various points they have kicker magnets which bring the two anti-parallel beams into collision. So they essentially kick the protons into collision in the hearts of the experiment. So LHCb, like Atlas, like CMS, just requires those beams to be circulating, and obviously the patterns are set up in such a way that most of the bunches cross at the experiments, but then they're kicked into collision by little kicker magnets near the experiments to actually get the collisions in the hearts of the various detectors. So there's no real special mode for LHCb. LHCb can be running while Atlas is running, while CMS is running. There's not a dedicated run for each particular experiment.
Okay. And so is this a single measurement? Is it just designed for this one specific measurement, or are there other measurements that you do at LHCb besides? So, because it's basically looking at bottom quark decays or beauty decays, right?
So a hell of a lot of decays, lots of different decay modes for a start. So for example, my decay mode that I was looking at was the decay of D plus mesons, right? So lots of different decays in bottom and charm. Charm decays tend to be more frequent but have smaller CP violation effects in them, whereas B quarks are produced less frequently but have larger amounts of CP violation in them. General case. So we look at the decays of lots of different types of particles and try to look for those CP violation effects. CP violation, for anyone watching, is any difference in the decay rates between a particle and its antiparticle. So a D meson and an anti-D meson, for example, looking at differences in their decay rates. And there's thousands of analyses, loads of different particles. Another analysis that came out recently was looking for exotic states of matter. So Lhcb found the first pentaquark, for example. When I was at university, it was always everything's either mesons or baryons, and then suddenly we got this packaging in pentaquarks at Lhcb, which makes things all a little bit more complicated.
Yeah, so generally particles, like meson particles, like middle-sized particles, are a quark-antiquark pair.
Yeah.
And baryons, which is everybody else, is a three-quark set,
quarks.
a three-quark ensemble.
Correct.
Of all either matter, or if it's an antibaryon, all antimatter, as opposed to a particle-antiparticle or a quark-antiquark pair. And a pentaquark is kind of both of them together.
Yeah, and Lhcb found you could have essentially a bunch of 5 of them together, which makes things a little bit more complicated.
Yeah, so you'll have 1 antiquark and then 4 quarks for the pentaquark.
Or do you have a quark-antiquark pair and then 3? I'll have to check. But you can essentially have a box of 5, which people had thought wasn't possible. Everything that had been found before Lhcb was either a hadron or a meson, as you said.
To establish a pentaquark, does that mean that what you have to do is you have to demonstrate that it stays as an ensemble until it travels some distance before it decays?
I guess so. I would have to have a look back at the specific measurement. I haven't looked at it for a long time. But I guess so, right? Because anything needs to have a significant lifetime to be able to be said
Claimed
to
as
have
a particle.
existed and be named as a particle. Now, I believe that length of time is fairly arbitrary. It seems to get shorter and shorter as we're able to measure shorter and shorter. So maybe we're just manufacturing particles out of nowhere, but I would have to check exactly. But presumably there's some minimum arbitrary limit that they've set on time. Otherwise it makes no sense, because the thing has to exist for a certain set amount of time.
Okay, so Lhcb, you were looking specifically. Now, why is it? Do you know why it is that the bottom quark and the charm quark don't have the same? Like, why does one have a stronger CP violation than the other? Now, the CP violation just in general is important, because if there weren't CP violation, then we wouldn't be here. CP violation is presumed to be what allowed the asymmetry in the production of particles and antiparticles in the early universe, and as a consequence allowed there to be an excess of matter, as opposed to an equal amount of matter and antimatter. And that small excess of a part per billion is what eventually allowed stars to form and things like that. Otherwise, all the matter, the universe would be just filled with photons. And so finding sources of CP violation is kind of a big question in physics, because it gets to the heart of why do we exist in the first place.
Exactly. So it was a really nice thing to study and say, look, I'm looking for the origins of the universe. Why are we even here? Didn't find anything in the end in the PhD, but it was a nice little tagline to put with the experiment. In terms of why there are different amounts of CP violation, in terms of the standard model in different sectors for the bottom and for the charm, you have to go back to the CKM matrix. So it's a long time since I did this theory-sided stuff in my dissertation, I guess, last when I looked at it. But if you go to the CKM matrix, you might be able to bring it up. Kobayashi, someone, and Muskawa matrix. I forget the K. Apologies.
So there's a great figure that they usually put in the. Yeah. Okay. I'm going to steal whoever person this is. I think this is right.
So CKM is it Kabibo, Kobayashi, Muskawa, I think. If you can, I don't know if you've got a.
So the particle data group has basically how the quarks mix with each other.
Yeah.
The matrix itself is just a set of 9 numbers.
A set of 9 numbers. Yeah. But the contributions in that matrix, which are determined, a lot of them just simply from experiment, essentially determine the amount of CP violation we're seeing in those sectors. But it's difficult to know them from first principles, some of them. So it's still an open question, really, as far as I'm aware.
So the Cabibbo angle.
So the Cabibbo angle.
That's not the same thing as or is it the same thing as the weak mixing angle?
Yes. Well, no.
No,
But it's what it is. It accounts for the. Well, it depends. Some people call these things different things, but it controls.
Oh, it's the mixing of the down quark and the strange quark.
Exactly. It controls the cross-generational interaction of quarks in various decays. So if you have a
so let's see. So what's going to happen is that you're going to produce particles in a pure state of some sort.
Yeah.
And then they propagate.
Or they interact.
The mathematics of the propagation is in a slightly different state. It's a superposition.
That's right. They interact as a superposition of those of those states. So
and the amount that they overlap tells you when you actually make the detection tells you the relative probability of seeing one type or the other.
Exactly. So if you couple within the same generation, you'll get a factor of cos theta, where theta is some small angle, so it's close to 1. But if you couple across a generation, so let's say up to strange, then you'll get a factor of sine theta, which is obviously theta being close to zero, close to 0. So we call it Cabibbo favored or Cabibbo suppressed. If you're Cabibbo favored, the interaction is more likely to happen. And if you're Cabibbo suppressed, obviously it's less likely to happen. And in any interaction, you obviously have to square that because you're taking the square of the interaction, the square of the matrix element. So it becomes sine squared or cos squared. So you can get very strong suppression of certain interactions and very strong sort of propagation of certain interactions because of that value of the Cabibbo angle. And the CKM matrix is essentially extending the idea of the Cabibbo angle out across all three of the
generations. So you're going to have what, three mixing angles and a phase.
3 in a phase. Yeah, I forget my matrix algebra, but I think it's 3 in a phase. Is like the minimum you can break it down to this Wolfenstein parameterization. It's a long time since all that theory stuff was. I have this thing pulled up
that has. So you've got 3 different components. They mix different. So 2, 3, 1, 3, and 1, 2.
Yeah.
And then the phase is this delta quantity.
Yeah.
And delta. So the CKM matrix is for the strong nuclear force.
So delta is the secret source where the CP violation starts turning up.
Okay, and then there's the equivalent of the CKM matrix that's the matrix for the weak particles. So that'll be the
PMNS matrix, I think.
Yeah, I don't know what it's called, but it's some. But it also has basically 3 mixing angles and a CP violating phase.
Yeah.
Okay. All right. So so keep going with. We're measuring the CP violating phase because the more CP violation that we discover, the more we can rest assured that we are actually here to begin with, that there is matter in the universe and that we're made out of it.
That's right. The problem is within the standard model, even if we were to find all of the CP violation that's allowed within the standard model, it still wouldn't be enough to account for why we're here. So a lot of the things we were looking for in Lhcb are other sources of CP violation that must come from physics beyond the standard model. So we need new sources of CP violation to be able to support the idea that that initial discrepancy in the early universe did come from CP violation.
Okay, so does that mean that this delta quantity, we already know what the delta quantity is?
Well, we have, I believe they have some calculation of it somewhere. But within the standard model, there's not enough room for CP violation to explain the universe that we see out there. So we need new sources of CP violation. And there's various mechanisms, esoteric mechanisms in the theory where this could come from. Obviously, the job of Lhcb is to go out and find these sources. And then the theoreticians can say, I think that might have come from here. I think this might have come from here. And then try to put it all together.
So 1 second. So the CP violation that we've observed is probably strongly constrained by the dipole. What is it? The EDM, electric dipole moment of the neutron.
I haven't looked at that for a while, but
So because
you go ahead.
The reason for one of the dark matter candidates is the axion, and that was proposed in the 1970s as a way to explain the absence of CP violation in the strong force. Like we expected a large amount of CP violation in the strong force, and we got none, or we got very, very little. And so does this new result point towards CP violation, some new source of CP violation that we hadn't seen before?
Not that I'm aware of. I haven't linked it back yet to CP violation.
Okay.
Somebody comment in the stream. CP violation. Is this an Epstein stream? I think CP violation does sound like, something that someone gets up to in a toilet. No, so CP violation is simply the differences essentially between matter and antimatter and how they behave. It's nothing more sinister. It does sound like something you get in trouble with the police for, but nothing too sinister.
Okay, so tell me. All right, so let's now turn to what is the result that came out.
Yes. So
from Lhcb.
So the result that came out, I'll just go back to slightly again. So we were having decays of beauty quarks, essentially these beauty quarks which are inside these B plus mesons. And what was observed is that when these B plus mesons were decaying, they were decaying more often to pairs of electrons than they were to pairs of muons, or vice versa. I forget which way up it was. But the point is, in the standard model, because W bosons couple equally strongly to electrons and muons, a concept we call lepton universality. So essentially the standard model treats all of the leptons, the electron, the muon, and the tau the same in terms of the fundamental forces. Because we expect that, we expected to see the same amounts of decays of these B mesons to electrons and muons, and that's not what we observe. So these results seem to suggest, at least at the 3 sigma level, that there's a breakdown of lepton universality, and these mesons and beauty quarks are preferring to decay to muons over electrons, which is, or electrons over muons, I forget which way up it was, but there's a discrepancy between the two. And that's not something we should see in the standard model.
Now, does that imply that it's actually an issue with the B quark, or does it imply that it's actually an issue with the W? That the W actually has a preference in how it decays?
I don't know if you could separate out the two because it's the interaction. So I think you would just say the interaction seems to have a favouring for one or the other. One of the things that they've suggested that could get over this is a lepto quark, which is a mixture essentially between a quark and a lepton, which I'm not at all familiar with and haven't done much research into. But essentially, the idea would be that the force itself, so I guess the W boson, is treating these leptons differently, which is not something we would expect.
So if that were true, then any way to produce the W, any kind of decay, would... okay, so it has to be a decay from like a quark. It has to be a decay from a quark. So it wouldn't work with a decay from like a muon or something like that.
Well, so what happens in this decay, you can imagine, I don't know if you've got an image you can bring up, but you can imagine the B couples to a W and, changes to some other type of quark. And then the W is spat out, and then the W couples to, a pair of electrons or a pair of muons. I don't know if you've got the Feynman diagram for it.
I can draw it. I'm pulling up a drawing pad so that I can draw one.
I can probably.
So so if it is a property of just the W particle instead of a property of the quarks themselves, then then you could get the same result if you just produced a bunch of top quarks, or not top quarks, but tau.
Well, so you would
Particles.
expect if there's a violation of lepton universality that it should show up in other instances, right? And there's other experiments and there's other measurements that have been made over the last sort of few years at LHCb and other experiments around the world that have all got these sort of 1 sigma, 2 sigma, 2.5 sigma values that might point at lepton non-universality. But
Okay.
none of them.
So let me draw the Feynman diagram you described. So you said that you come in with a B.
So I can send you the link with the thing as well.
And then it goes. What does the B decay into?
So you can imagine the B comes in. So here it's got a B bar, so an anti-B,
Okay.
and then there's a loop. So maybe I should send you it's essentially a loop diagram. So I need to. I might have to send you the link here so you can have a quick look. So if you have a look on there, you can see the Feynman
All right, let me
diagram.
pull that up.
And if you can pull that up and we can discuss it.
Okay, hold on. That failed. Let's try one more time.
Did you get that?
I got the link. So I'm pulling it up.
So the B essentially decays to another type of quark, splitting out the W, and then that quark throws off a photon or a Z boson, and then
All right, what page is it on?
It is on page number 1.
Oh, right there, page 1. Okay, so U B bar, you get this. Oh, so it's a Z particle.
Yeah, and it's the
So
Z
it can
or the
be-
photon that decays to 2 leptons.
All right, so and then what's this LQ?
So
Oh, that's the
LQ
lepto quark.
is the
Okay.
lepto quark, the potential explanation for how this happens. So you have the B bar
All right,
comes
so you have
in.
a B plus going into a K plus, and then you have this B bar that decays in this loop to up charm or
Well, so it doesn't decay, but it just spits out
right.
a
Okay,
photon
yeah.
or a
The
Z.
loop. It's a bunch of virtual particles, right?
Yeah,
So,
it's a bunch of virtual particles. So don't worry about too much about what's going on inside, because
then
anything's
it's the
allowed to happen.
Z. It's the Z particle that actually decays.
And then the gamma or the Z or the Z0 decays to the 2 leptons. And the
Okay.
point is in this interaction, it should, the L plus L minus at the end should be equally likely to be electrons, a pair of electrons, so a positron and an electron, or a muon and an anti-muon. And we don't see the same rates for both of them when we correct for kinematic effects. And that's where the problem was coming in these results.
Mm-hmm.
Because in terms of the fundamental interactions that are going on, they're weak interactions, and then here's an EM interaction or another weak interaction. They should treat the leptons the same, and we find that they don't.
So the Z particle should decay into, as long as it has enough energy, it should decay equally into muon, anti-muon, electron, positron, or
Correct.
tau, anti-tau.
Correct.
And the fact that it doesn't implies either something is going on weird with the Z, which is this theory suggests would be unlikely, and instead, or maybe that it would be, even if it was, we would interpret it as. So another way to conceive of this would be that we interpret the Z interaction is the component of the interaction that always works, and that there's some other force that's going on here, some other particle in here that couples more strongly to muons or electrons than it does to the counterparts.
Yeah.
So in this case, the figure on the right, that decay favors one type of, or this process favors one type of decay or one type of byproduct more than another. And that's where the asymmetry arises.
Correct. So the one on the right is is a hypothesis about how this problem could be answered. So the left is the standard model interaction, what we would expect to happen. And then the little diagram on the right there with the LQ, the lepto quark, is a potential diagram that could interfere, be an additional way for this interaction that could how it could proceed, that could lead to the discrepancy that we see in the results.
Mm-hmm. So what I wonder, so the implications, if there was a Lepto Quark, the implications would actually have probably significant effects in the very early universe when all these things are happening. Okay, interesting. So the result was they saw this asymmetry, and now we need to do two things. One is come up with possible explanations that might have other observable consequences, and take more data so that we can determine if it's a statistical anomaly or if it's the real thing.
Yeah, exactly. So a lot of these measurements, as I was saying, there've been various measurements over the last sort of few years that seem to point at, little discrepancies in lepton universality, but they always seem to be about the the 1-2 sigma, and they don't really go anywhere, or they appear in the data and then they disappear. This is the first one, as far as I know, that's sort of around that 3 sigma level plus. So people were getting a little bit excited about it, particularly as it shows a pattern with other results. So people were sort of...
Yeah, okay, so it's not the only hint that we have.
It's not the only hint, but so people were getting this, cautiously excited phrase out in sort of, Cerny Twitter.
Yeah, okay, now one quick thing. So a question came up that's like, what's a virtual particle? So when you have a Feynman diagram, like the ones that I'm showing, the particles that end, where like you can see the end of the line, so the up quark, the bottom, the B minus or the B bar quark, those are real particles. Those are particles that you produce that can appear in a detector. Anything that has where it doesn't terminate, where the line that indicates the presence of the particle doesn't end, but is actually connected to the rest of the diagram, those are virtual particles. So virtual particles are particles that exist only within the interaction. And the real particles are the ones that can basically, in the diagram, can go off to infinity.
Yeah. So the real particles, if that's the right word, the real particles are the ones that you see going into and coming out of the interaction, and then the virtual particles, are essentially the mechanism inside. You never see them. You couldn't catch them. You couldn't use them. But
and as a consequence, the virtual particles can have unique quantum. So quantum mechanics allows virtual particles to behave somewhat differently than real particles, in that they can appear to violate certain rules of quantum mechanics, like what their mass is, for example. But because they never make it outside of the box of the interaction, you never actually see it.
They never change any real physics, quote unquote.
Yeah, they don't change anything that you observe from the outside.
So it's a little bit of a black magic box inside the interaction.
Yeah, so a follow-up question was, why differentiate virtual particles if you can't detect them? And that's precisely the reason, that you can't detect them. And so real particles are particles that you actually can detect and that you can actually produce, and virtual particles are the ones that you can't detect. And as a consequence, there are fewer constraints placed upon their behavior.
Yeah, so this, this...
Oh, and then another question that came up is what's the difference between these virtual particles and the Lepto Quark? And the answer is that we've seen, like, Z particles. We've seen a lot of the particles that are in these loops. The ones that are virtual in this particular interaction, we know what their properties are. And so the problem is that the observations that were being seen in this experiment disagree with what our understanding of these particles are, and as a consequence, we need to invoke some new particle in the interaction that would make the change, or like affect the change that we observe.
So this result was, it was all the rage about a week ago, and then it just sort of fell off the map because, a few reasons. One of them being the 3 sigma level. So a lot of particle physicists don't get out of bed for, less than 4 sigma.
Yeah, all the astronomers would be like, raving about this, and astronomy Twitter would be all over the place with the 3 sigma detection.
My biology friend was telling me about his amazing, p-values of less than 5%, and I was like, just please don't talk to me about these 2 sigma things. There could be just anything. But yeah, a lot of particle physicists, not particularly interested. Down at the 3 sigma level, there was a little bit of, sort of hubbub about it in the media, but not too much. And then, as I say,
yeah. Now, part of the reason, I guess, for the audience that 3 sigma doesn't really excite particle physicists or high energy physicists is because they see bazillions, I think is the right term, of collisions. And so as a consequence, there are many, even though something is maybe only 1 out of 1,000, like the probability of something happening is only 1 out of 1,000, when you're running bazillions of measurements, those 1 out of 1,000 things can happen with uncomfortable frequency.
Yeah. When you're running thousands and thousands of measurements, they come up more often than you'd expect. There was a link on the blog, the Quantum Diaries, just saying like, look, here are this year's 3 sigma effects that have come and gone, because it's a very common thing that these 3 sigma variations arise, and then we take a little bit more data and they go away because they were just fluctuations in the data. So when we're at 3 sigma, people start to get interested, the interest starts to go up, but nobody's really biting yet. It's when you start to get sort of 4 sigma and above 4 sigma, getting towards that holy grail of 5, that people really start to take interest, as we'll come on to with the g-2 results.
Okay, so this is a good time to pivot then.
All right.
Unless there's more to say about the this Lepto Quark. But
it
would be.
I think the thing with this is we're just going to have to wait, aren't we? Because it's a 3 sigma result. There's going to need to be a lot more data taken. Lhcb is not going to run again until next year, so you're probably not going to have any follow-up on this for at least a year and a half, 2 years.
Now, does that mean, is it not going to run again simply because the LHC is going through an upgrade?
The LHC is not running, right?
Okay.
The LHC is not running now, as far as I'm aware, and then it will come back online next year. With
are they doing an upgrade? Is that what's going on?
LHCb upgrade, yeah, will be online, so they'll be able to take more data. Now, how long it will take them to turn around the analysis, I don't know, because I'm not close enough to that analysis to know. But I imagine if it's not running until next year, it's going to be the middle of next year at the very earliest. So a year at the very, very earliest before we find out anything more about this. And given it's 3 sigma, I think most people are just like, let's wait and see.
Yeah.
And even then, we would need independent verification. So
what else could do this? Is there another B factory somewhere that can do
this? There's the one that is, I forget the name.
Is there one in Italy?
Now. Over in Decay, is it? There's Bell 2, right? Bell 2 could probably do it.
And where's that? Is that?
It is over at. I always forget where Bell 2 is. Is that the one that's over in Japan? I think. Bell 2. Bell 2 is Super B factory for precision measurements, which is over at. Where is it now?
Japan. Tsukuba Ibaraki.
Okay, so it's over in Japan. So they probably would be able to do this, I imagine. Okay. So we need the independent verification. We need more data as it is. So it's going to be a little bit of a wait on this, which is why I think people have pivoted pretty hard to the g-2 results. Because, listen, in particle physics, it's been a slightly lean period, right? You've had people saying it's the death of particle physics. There's nothing that we're going to find, in the years upcoming in particle physics. Is there any reason to have a new, larger LHC, given that we, didn't find all the supersymmetric particles we thought we were going to find at the sort of the energies we were working with? People have been talking down particle physics. It's been a little bit of a lean period. So anything that comes along that suggests new physics is something that gets particle physicists very sort of excited. So they were excited about this last week, and as I say, a lot more excited about the g-2 results, with them being up at 4.2 sigma now. So maybe let's have a
So I have a graph or a picture of the ring as it arrived at Fermilab. So this was almost 10 years ago, not quite 10 years ago, that the ring arrived at Fermilab. It was originally to make the same measurement at Brookhaven National Lab. They used this device and then they were going to do it at Fermilab because Fermilab is better than Brookhaven, or as the rest of the world, as far as the rest of the world is concerned, it's because Fermilab has a more intense and a higher energy beam. And so like the beam properties that you can get at Fermilab are different than what you can get at Brookhaven. And so so they sent this ring that they're using to make the measurement, shipped it to Fermilab, and it really reminded me. So it starts in Long Island. You have to go, like 1,000 miles maybe to get to Chicago. But because it's a precision instrument, it's not something that you just stick on a truck and drive through the Appalachians. And so the path of the muon g-2 ring, see if I can have a map, pull up a map.
So it started off at Brookhaven, didn't it? Which is whereabouts is Brookhaven in America?
So that's on Long Island.
On Long Island, and then they took it down on a big boat all the way down the east coast of America.
Yeah, all the pictures that they're showing are showing the results that just came out. So had I looked at this a week ago, I would have been able to. The map would have been the first thing that comes up.
And then up the Mississippi River, right, on a big barge. To get it as close to Illinois as they could, which I guess you can get quite close, right? You can go all the way up to. Can you get how? I don't know.
You can go. So there's a canal that connects the Chicago River to which. So the Chicago River used to feed into the Great Lakes. Now the Chicago River runs to the Mississippi. Fermilab. So anyways, the Mississippi River is connected to the Great Lakes. And so they're running on I can't remember what the canal is called that connects the two. And this map is still not showing up. So anyways, people will just have to trust me that there was a big map to bring the ring. Oh, here it is. To start from Long Island, down the coast of the United States, up the Mississippi River to this canal that connects it to the Chicago River, and then they took it off and they drove it the last little bit on a truck, and it was a gigantic truck. So the transportation of the muon ring g-2 Fermilab. I'm putting in just a bunch of keywords to see if the right images come up. Okay, here's a good image.
So I can show people watching mine an image of them moving the ring. If I can bring it up in big, I can get a nice big image of it.
So they closed the freeway down. They did it at night. They closed the freeway down. They were driving at like probably half a mile an hour, kind of like taking the space shuttle out to launch. And it had 8,000 tires underneath it to keep it steady. Because anytime it, something gets bent out of shape, that's a lot of money to get it repaired and make sure that it's working properly and everything. And they also, and this is probably the most amazing thing about the transportation of this ring, is that they opened the south gate to Fermilab. So Fermilab has 3 gates to it, one on the east, one on the west, and one on the south. And a bunch of people who had been at the laboratory ever since the 1970s. I mean, these are people whose employee numbers are like in the single digits. They were saying, and I was like 12,000. I was employee 12,000 who had gone through there. So one of them was like, I've never, my whole time here, I don't ever remember having the south gate ever be opened. And so it was, locally it was a big deal for the people at the laboratory. Like, wow, they're opening the south gate to get this in. So they drove it up and brought it into the laboratory, into a complex that they had been kind of preparing for near the main building on the Fermilab campus. The Wilson Hall is the main building at Fermilab. But it reminded me, the transportation of this ring reminded me of the transportation of the Catron experiment. So the Catron experiment is designed to measure the masses of neutrinos. Let's see, transportation map. And it was fabricated, the main part of the Catron experiment was fabricated in Germany. And the experiment itself was going to be run also in Germany. But because of how precisely the thing needed to be maintained, you didn't want to drive it across the roads, or you wanted to do as little road driving as possible. So it was built just north of Munich in Deggendorf, and it was sent down the Danube River into the Black Sea around the Mediterranean, up to the Rhine River, through Belgium, to get to Karlsruhe, Karlsruhe is a German city that's right on the apex of the Alsatian corner of France. And so it went up the Rhine River, was offloaded at Karlsruhe, and driven the last, I don't know, few kilometers to the place. And the size of the Katrin experiment was dictated by the space between the buildings in the street that they had to drive on to deliver it to the experiment hall. And so there's a fantastic picture of Katrin experiment as they're driving through the last neighborhood, squeezing it in between the buildings. So this is the, so when they transported the g-2 ring from Brookhaven National Lab over to Fermilab, it was basically the same thing as the transportation of this Katrin experiment. Maybe I should share this with you.
You can share it if you can share screen, and maybe we can see.
Can I share my screen? I can probably.
So if you go down to the bottom right, there should be a share screen, and you can just share the screen from there.
Is that this? Okay, there's share screen.
We should be able to see.
You can see the whole screen.
Yeah. Oh, wow. So they really had to squeeze it through the neighborhood.
So that's the Katrin experiment. And then the Fermilab, the delivery of the ring at Fermilab was kind of similar, where they had to shut everything down. A whole bunch of people turned out to watch it come in. It came pretty early in the morning, right? If they're going to shut the freeway down in Chicago, where there's 10 million people, they're going to shut it down at 2 o'clock in the morning.
Yeah.
But the Katrin experiment, so here's the path, starts here, and instead of driving the 300 kilometers, they send it down the Danube and all the way around all the peninsulas of Europe, and then
just to go that 500 miles, if that, you could have done on the road.
And then this was it, going into the Karlsruhe Institute of Technology, I think is something like that.
Oh, wow.
And then there it is. And
quite the trek.
So that limited the size that they could make this. It's a big mass spectrometer. It limited the size that they could make it was that piece.
Amazing.
Okay, so g-2, back to this. What is this experiment for, and why do people care about it?
So what we're looking at here is the magnetic moment of the muon. So the muon, for those out there, is essentially the heavier cousin of the electron. In terms of force, it behaves very much like the electron, but it's just, I think, 200 times heavier, significantly heavier. So it's the heavier cousin of the electron. And its magnetic moment should be around 2. This from calculations from the Standard Model from quantum physics. But because the electron also has a magnetic moment, and it's also around 2. That's right. And what we know is that actually it's very slightly different from 2. And the reason it's slightly different from 2, its magnetic moment. In terms of magnetic moment, think of it like a little dipole magnet, right? The muon behaves like a little dipole magnet, and it can spin around in a magnetic field, and it makes its own little magnetic field. Now, what we know from particle physics is that the value is actually slightly different from 2. And the reason it's slightly different from 2 is because the magnetic moment of the muon is changed slightly by all of the virtual particles that are popping into and out of existence around it in what we call the vacuum. We now know the vacuum isn't actually a vacuum, it is an empty space. There's all these particles popping in and out of existence in the Standard Model and interacting with that muon, which changes its magnetic moment. And depending on how many particles and what types of particles are popping into and out of existence in the vacuum, that changes the value of the magnetic moment of the muon. So if we can measure the magnetic moment of the muon very, very accurately and predict it very accurately with theory, if we see any discrepancy between the two, it must be because there's different types of particles or new physics popping into and out of existence in the vacuum. So it's an indirect way of measuring if there's new stuff and new particles out there in the vacuum.
Right. So now the G-2, so that's the reason it's called G-2, is that you expect it to be 2, so you subtract 2, and whatever's left over is the new physics. Or at least the physics that's higher order in the nature of the interaction. Now, in the electron G-2 experiment, there were some really precise measurements. That's like the most precise measurement that's been made in any science ever in the history of ever. Was the electron G-2, because the calculations were done to 13 decimal places, and the experiment was done to 13 decimal places. And that was actually the Nobel Prize. So the University of Washington, which is where I went to graduate school, they have 2 Nobel Prizes in the physics department now. One of them was, the first one was this G-2 experiment by Hans Dehmelt and his group. And so it was after that experiment that we got our new physics building. So they called it the house that Dehmelt built, was the electron G-2 measurement. So this is a muon G-2 measurement, which is harder to do. The advantage you have with the electron G-2 measurement is that you can have an electron in a trap and you can keep it there forever, as long as you want. The challenge with a muon G-2 experiment is that when you make a muon, you have 1/1,000,000th of a second to make your measurements.
Before it decays away.
Before the muon decays away. And so the only way to keep the muons around long enough to make this measurement is to get them going at high speeds, because at high speeds, the muon time dilation makes it so that the muon lives longer. You get relativistic effects that make it so that the muon lives longer according to our clocks. Its internal clock is still 1/1,000,000th of a second.
As I understand it, they even go further than that. So they get the instantaneous pointing of the magnetic moment from the energy and the position spectra of its decay product. So the positrons that hit the wall, essentially. So they even have to look at some of the decay products. You're right, because keeping muons around for very long is not particularly easy. So you'll know about this as well. The way they do it is they stick all these muons essentially in a big storage ring and shoot them around, and they have a very high magnetic field, which essentially makes these magnetic moments, think of the muons like little bar magnets, spin around like a top, what we call precession. And we can measure how quickly they rotate around or precess. And therefore, we know if we measure the magnetic field in the experiment very accurately, the only thing that affects that precession speed is either the magnetic moment of the muon or the strength of the magnetic field. And if we know the strength of the magnetic field, we can therefore get an idea of the strength of that magnetic moment of the muon from how quick they're spinning around. And that's what they try to do in the experiment.
So they call this a storage ring. Just so that everyone's aware of what it means to store a muon. These muons live for about 60 microseconds. Not about 70 microseconds. It's actually it's 30. The gamma factor was like 34 or something like that. They tuned it to have a particular term cancel out. So a gamma factor of 34 means 34 times 2 microseconds is 70 microseconds. So they circulate around many times because they're traveling at basically the speed of light, 99.97% the speed of light. So they're going around really fast, and they do multiple loops around this ring, but they don't stay in the ring for very long. Okay, so this is looking at when they have these muons that are going around. When the muon does decay, it's going to decay, because it sounds like they were using positively charged muons. Is that?
I'm not sure. Do they use anti-muons or do they use muons? I'm not sure.
So I guess it doesn't matter. So the muon is going to be there. It's going to be circulating around because of this magnetic field. When the muon decays into an electron or positron, whatever it is that it decays into, it has the same electric charge. Because that particle has a smaller mass by a factor of 500, it's going to spiral in very quickly. It's going to lose a lot of energy due to synchrotron radiation, and it's basically going to dive into the wall. And so they have all around the interior of the ring is a bunch of detectors, so that when the muon does decay and then that particle slams into the wall, the decay particle slams into the wall, they can detect the location of where the decay took place, and I guess presumably measure some of the spin properties of the.
Yeah, so they can get the instantaneous pointing of the spin of the muon. And then if you look at that instantaneous pointing at a set of points around the ring, just like taking snapshots, photos of it, you can get some idea of how quickly it's processing around, how quickly that spin direction is changing, I guess, in a simplistic way. So once you've got that idea of how quickly these muons are spinning around or processing, you can make that measurement of their magnetic moment.
Okay, so there was a picture that they showed in the live stream that was this wiggling decay.
Yeah. Do you want to share that, and then we can have a?
Let me see if I can pull that up. So they have a bunch of images that show how they measure the magnetic field. Here is the wiggly decay, a low resolution version of the. Okay, here's a high resolution. Wow, that's a really high resolution version. This will be great. All right. Well, it looked like it was a high resolution version. I guess I clicked on it too soon. I hadn't loaded up all the way. Let's try one more time. 4,000 pixels by 3,000 pixels. So that's the real deal.
That sounds decent.
Maybe we'll just steal this one from the archive. That's better.
I'll pop it up on the screen and we'll chat through it.
Yeah. Okay. All right. It's not that much better, but here we go. I'll pull it up. And I'm going to switch it to just the window. How do I? Oh, I can slide this. No, I can't.
Well, we can see.
It's not letting me.
It's all right. We can see the wiggly plot. So maybe if you want to explain what the plot is showing.
Hold on, I just ruined it.
It's all right.
Oh no, it's still there.
Still there.
It's still there.
Yeah,
Okay.
it's still there.
So this plot shows the counts per nanoseconds, counts per 150 nanoseconds. So they're binning it up in 150 nanosecond things. The population of muons is decaying constantly over time. So basically what they do is there's a 150 nanosecond window, and then it gets to the end, and where it ends on the right is where it starts on the left.
Yeah.
And that's the next 150 nanoseconds, and then it goes to the next 150 nanoseconds or something like that. So this is, you can see that the decay rate is slowing down. As the population diminishes, you go from one level to the next, to the next, to the next, down until you get basically down into the noise. So you can see the error bars growing on the very bottom thing. You can start to see the error bars in the data that indicate that the population is getting really small, and so you have larger statistical fluctuations. The oscillations up and down are a consequence, I guess, of the spin state of the muon. Is that right?
That's how I read it watching the.
Let's go with that. So the muon is precessing, and as a consequence, when the decay products come out, you're going to get more or less depending upon how the spin is oriented relative to the magnetic field. And so the oscillations here is the precession rate, and then the decay is the fact that after some number of, after a period of time, the population of muons is going down, and so instead of having one long, really skinny graph, they chopped it up into a bunch of pieces.
So you can imagine, and I think was it Chris Polly? I think he showed this simple model in the seminar. You could fit this graph with essentially a cosine component, which is the wobbling up and down, and an exponential component, which is the decay away of the muons, and that cosine component, which is the wiggling, has your omega inside as its
the precession frequency
as the precession frequency. So looking at this graph and looking at how quickly it wiggles up and down, you can get an idea of how quickly the muons in your experiment are processing around. And because you know how quickly they're processing around, and you know the magnetic field that you're applying to them, the only other factor involved is the intrinsic magnetic moment of the muon, which you can now estimate. So this is a really important graph.
This measurement, they have to be so precise in the measurement that after they run, is it every couple of days? So they'll run the experiment for a while, and then they'll stop, and then they'll remeasure the magnetic field.
Yeah.
And then they do it again, then they remeasure the magnetic field. So they're constantly measuring, probing the magnetic field, making sure that they understand if the temperature changes a little bit in the room or the humidity changes in the room, how the system breathes, to know that the magnetic field is not changing in a way that they don't understand.
So exactly right. So if you looked at if you watched the seminar yesterday, there was about 15 real world factors on the end of this that they check for the systematics. So the temperature of the ring, as you say, which might change the magnetic field, the electric fields they have to apply on the top and bottom to keep the muons confined vertically. Any sort of shaking or mechanical vibrations of the system, all these kind of things that you have to keep in mind so that you know exactly the magnetic field that you applied to your muons. Because if you don't know the magnetic field you're applying to your muons, well, the effect that you're seeing could be either due to a change in a magnetic field or a change in the magnetic moment of the muon, and you don't know which one it is. You need to fix one very, very precisely so that you know that any discrepancy must be in the intrinsic magnetic moment of the muon.
Yeah, and that was something that came out in their discussion of the results, is that the systematic uncertainty, let me see if I can find, they have this figure right here. So the error bars that are shown have two components. One is the extent of the bar itself, and the other one is like the vertical hatchings on it.
Yeah.
And I guess the statistical error is the vertical hatch marks. So the statistical uncertainty is given by the error bar that is between the vertical pieces.
So maybe if you explain briefly what this shows for the people who are watching. Sorry, I didn't mean to go across you there.
Yeah, okay. So this is whatever alpha mu is. I believe
that's the anomalous magnetic moment. So
okay,
basically taking away the 2, which is the boring, standard model stuff.
Okay, so you subtract 2 from the magnetic moment that you measure, and this is the difference between the two. So this is g-2 basically.
Yeah.
And it's a small number, right? It's g-2 minus 1.165 million.
Yeah. So this is taking away all the other boring stuff that's not,
so these are parts per million. This is like 18 parts per million is the prediction from the standard model. And what they measured is something that is 20 parts per million. So 18 versus 20 parts per million doesn't sound like that much difference, except that their error bars themselves, like their uncertainty in their measurement is, it looks like about a half a part per million. So 500 parts per billion is the size of their error bars. The error bars have two components. One of them is the error bars that come with the fact that they don't have an infinitely large sample, right? They have some sample size, and as they take more and more measurements of their sample, then it's going to decrease, like the statistical error is going to get smaller. So it's very easy. It just takes time to bring the uncertainty in the vertical error bars together. To shrink that uncertainty just takes time. If you want to shrink it by a factor of 2, you have to take 4 times as much data. But the systematic uncertainty, so that's the uncertainty in your measurements of the magnetic field, it's your uncertainty in the behavior of the animals crawling around the room, it's your uncertainty in the behavior of the placement of the furniture that's in the room. So all these systematic uncertainties, the temperature variations, how well can you calibrate the probe that you're using to calibrate the magnetic field, those systematic uncertainties, that is the full extent of the error bars. So when you go all the way to the ends of the error bars, that includes the systematic uncertainty. And an important, general experimental fact is that once your statistical errors become the same size as your systematic errors, then you're basically done with your experiment. There's no way to make improvements. Any improvement that you make on the statistical side is going to be far outweighed by the uncertainty that you have on the systematic side. And so you basically design an experiment to limit the systematics, and then you run the experiment for the length of time that it takes until the error bars from statistics are similar to the error bars in the systematics, and then you design a new experiment. And so that was what was done here, is that it shrinks, the Fermilab result shrinks somewhat. It's like a 25% shrinking or something like that of the systematic error bars. And then they have their statistical error bars are basically the same size, but they both agree with each other. The two independent measurements, the measurement that was done at Brookhaven and this new measurement that was done at Fermilab with a different energy properties of the muon beam agreed with the Brookhaven result.
So what we're seeing here, very simply for people, is that the mint green line is what theorists predict the magnetic moment of the muon should be, quote unquote, should be, and then the results on the right in the sort of purpley pink color are what we've actually seen from experiments. So there's a big tension between the two. They don't particularly well agree with one another, and it's becoming more and more unlikely that this could just be a statistical fluke. 4 sigma now.
So you have to go. So here's one error bar. You have to go 4 and a little bit times that error bar in order to get into this green area.
So it's becoming less and less likely that this could just be a fluke, and more looking like there's a problem between our theoretical prediction and the experiment. Now, people have come out with a couple of reasons that could be. So some people have suggested that it's the standard model prediction that's wrong. And one reason for that is because it's very hard to make predictions of the magnetic moment of the muon, particularly the strong force interaction terms that go into predicting the magnetic moment of the muon. So I believe there's another prediction that is much closer to the experiment.
That's the one that was shared on Twitter yesterday?
Yes, the BMW collaboration, I believe. So there's some people saying that, look, this could just be a problem with our theoretical prediction of the magnetic moment of the muon. We don't know theory well enough. We're not doing the lattice QCD predictions well enough. That's a boring answer. I hope that's not the reason. I hope it's new physics, but it's a potential explanation. So maybe that one there, Joachim Kopp, if you go up. That one there, Joachim Kopp on Twitter. It's like second row, third across.
Second row, this one.
Yeah, is that the one? Yeah, BMW showing it's very close.
Okay, so let me pull this one up. So this BMW C,
or the
and
BMW
C20 right up at the
white
top.
paper 20. So there's some theorists who are suggesting that the way that they calculate the magnetic moment of the muon suggests that there's no real tension between the theory and the experimental results that we're seeing. Now, we should note that the mint green that we saw before has a lot of different theoretical predictions in it from different groups with different methods. So this is only one result, the BMW one, that's much closer to experiment, but it still could be that we simply have a problem with how we are theoretically saying what the magnetic moment of the muon should be.
Okay, so let me get that original picture back up. So this is the one that was presented yesterday, 1 day ago.
Yeah.
All right, so what you're saying is that the standard model prediction, the reason, so typically when you have a model, there's no uncertainty, right? The model predicts a thing, unless you incorporate like quantum effects or something. But in this case, the uncertainty in the standard model prediction is because different groups are using these calculations are not things that you go to the blackboard and run. These are calculations where you build a computer code that does these calculations, and it takes millions of hours of computation time to get through them all. And as a consequence, you have to make certain approximations, or you have to have certain algorithms that are going to produce the different results.
Yeah.
And so
that standard model prediction is an average of loads of different groups, models,
we're simultaneously working on like calculating this thing.
Yeah.
And so it's a theoretical uncertainty that's a consequence of the various approximations that different groups are making when they do the calculation.
That's right. However, there is one result in particular, this BMW 20 result, which would be much closer. It would live in that no man's land between the light green and the actual experimental result. So it could be that so the image that they shared had their result was like at this around like 19.5 to 20 parts per million, I guess. Exactly. So it could be that this is just a problem with our theoretical predictions. That's obviously the boring answer, and we have to be fair and say that, look, the standard model prediction that's been presented is an average of lots of different groups. So we can't privilege one result over another. We have to stick with that average.
So it's like polling data for elections, right? It's
Yeah.
an ensemble of like a bunch of different polls, and some polls are going to have
outliers.
So that would imply. So I guess what would be? Where's your money on this?
I mean, science is a conservative, endeavor. You have to sort of say, look, we don't know yet. So, I have to put the money on it being a theory thing. But I really, really hope it's new physics. And, maybe that's the wrong thing for a physicist to say, because I want the right answer. I'm not going to pollute the waters and say that it is something when it isn't. But I would like it to be new physics. Of course I would, because it's something interesting, something new. We're just going to have to suck it and see, I think.
Yeah, I guess you have the advantage of being an experimentalist, which means you can sit back and be like, well, we'll just take more data and find out. Where the people who, especially the theorists who do, not the theorists who do QCD, because so they already know what their job is. But the theorists who do like cosmology and astroparticle physics, they're like, here's new physics, here's all the possibilities, and here's how it's going to affect the growth of structure in the universe. To them, this is a playground. All the space between the experimental measurements and the standard model prediction, to them, is not an issue with their code. That's the playground that they have to go around in and come up with new ideas that can explain life, liberty, and the pursuit of happiness.
There's another question that sort of comes up with this, and I wanted to get your sort of thoughts on it as someone who was, more close to this experiment. You've got a Brookhaven result from 20 years ago or whatever it was. You've got a Fermilab result from recently, but which is essentially using the same equipment, the same methodology, the same approach. How correlated are those results, and how fair is it to simply take them as independent results? I'm sure this was taken into account in the analysis, but it strikes me that, are they not incredibly correlated? Because
so I guess it can depend, right? You're always going to store a muon in a ring. So like there's geometry issues to be perhaps concerned about. I suspect it's not like the spin of the protons coupling, or the spin of the muons coupling to the spin of the Earth, if you had some kind of weird spin-spin interaction. I guess that's a possibility, but it probably would have turned up somewhere else.
But is it fair to say that the Fermilab result is a new result, or is it just an emulation of the Brookhaven?
Is it a superposition of a correlated result
Correct.
And a new result?
Yeah, that's what.
So it's because the same thing arose with the Dhamma dark matter experiment, where they made Dhamma. They had some special kind of crystal that you can only grow in the orchards of northern Italy and the vineyards of northern Italy, and so they saw a signal. It's like some sodium iodide detector technology that no one else had built. So the Dhamma results came out like late 90s, and then they rebuilt it, the Lhcb experiment, using the same detector, and they saw the same signal. But no one else who is presumably just as sensitive, except they're using germanium or something like that, that they didn't see it. And so that's another example of an experiment where they built it, and then they built it again with using the same detector, not necessarily the same design or surrounding the detector, but the same detector technology.
Yeah.
And so, I think it's a fair point to make that they are using a lot of the same equipment. I think some of the differences, some of the things that I think would point to this as a completely independent result, if I were to argue for the defense in this case, would be that the beam's at a different energy. And there you go, the beam's at a different energy. They probably had different calibration things in terms of like what systematic effects might there be and how can we improve upon the calibration that they had before. So my understanding of like deciphering all of the stuff that went into the discussion when they announced the results was that the Brookhaven experiment, they had to measure also the electric field, like the local electric field. And as a consequence, they were limited to some extent in their uncertainty, their systematic uncertainty by their ability to measure that electric field, because they couldn't get the beam energy high enough to cancel that out. And where at the Fermilab results, they chose a specific beam energy specifically so that it would eliminate. You would, because it's basically, the term has an electric field and then a beam energy term, electric field term and a beam energy term. And
it was a term over like gamma squared or something. And if you make gamma big enough, it just,
and so, so they made gamma bigger so that the term drops out and it basically drives it to zero. And so that's something that eliminates one of the systematic effects that had been present in the Brookhaven result that's gone in the Fermilab result. And so I guess in all experiments, it's a matter of playing whack-a-mole with, as the sensitivity improves, as you eliminate certain systematic effects and your error bars shrink down, you uncover new systematic effects. Like there's some other thing that now you have to worry about the fact that, well, here's an example. In gravitational torsion pendulum experiments, there was the group at the University of Washington made an experiment where they designed like a bunch of pizza slices. So they had a puck that was a bunch of pizza slices made out of magnetic material, and they arranged the magnets so that the magnetic field would cancel itself. However, the way that the magnetic field was generated by the different material was, in some of it was generated by the orbital motion of the electrons, and in some it was generated by the spin of the electrons. And so you have spin component of a magnetic field and an orbital component of the magnetic field, and then you have them cancel each other. So the magnetic field cancels, but now you have a net spin. So you have a pendulum that has a net spin from the spin of the electrons. And what ended up happening was they started making measurements, and the spin of the pendulum, the spin of the electrons in the pendulum, coupled to the spin of the Earth. And so they're like, we get this really anomalous signal that points due south. And it was this spin-spin coupling of the pendulum to the rotation of the Earth, like the quantum spin of the electrons coupling to the rotation of the Earth.
That sounds crazy.
Yeah, I mean, so it's cool though, isn't it?
So it is a fair question of how decoupled these results are, and you make a good case that they are relatively decoupled. But in the end, it comes back to the same thing that's going to happen with the Lhcb result. If it gets up towards 4, 5 sigma, you're going to have independent verification from an experiment that has completely different technology inside, completely different methodologies for calculating this thing. So one thing people don't realize at the LHC is that we have Atlas and CMS. And when we discovered the Higgs, they both discovered the Higgs. So we had Atlas and CMS with completely different technologies inside them, different methodologies for looking for the Higgs, which independently verified that they'd found this thing. So you could have a lot more confidence that whatever systematics there were between the two were different, and you were still getting this result. And
the same thing happens with the results at Fermilab. They had the CDF and the D0 detectors that were designed to look for different processes. And as a consequence, when they did the analysis, it's like, well, we were looking at the interaction with the Hubble particle, and this other one was looking at some other kind of interaction that would both give you a signal, but through different processes, and then they could analyze them together. Now, so one of the questions came up is, all right, so they've made this detection. So what? So the G-2 disagrees with the theory, or at least disagrees with the ensemble of theories, if not with every individual. So one of the things that this does, I guess, is forces the theorists to get their act together in terms of, we need to come to better agreement between so we have 10 groups that are working on it, and we all disagree with each other to some extent. It hasn't been a big deal because there hasn't been any guidance from experiment. And now they have guidance from experiment. There are 2 data points that are that you have to contend with. And so that's going to drive the theorists to come to a better agreement with each other. So that's one consequence of this. That's a consequence that's perhaps only important to a few hundred scientists. So, but what about the physics? If this is a real anomaly that deviates from the standard model, then what?
Well, so it suggests that there's some other physics going on, potentially some other particle or some other force. As you say, not only does it force the theorists to get their act together, but it potentially gives some signposts for where new physics could be hiding. Now, I'm not very much up on my g-2 best theories that could have accounted for this experiment. But I'm sure there's a lot of theorists sat there going, well, my theory, would fully account for this. So there will be various theoretical frameworks that explain this particular anomaly and will, as I say, give signposts to where new physics might be hiding. I've heard people talking about potentially a second Higgs. We've talked about the fact that this could be an issue with the theoretical calculations. At the moment, it's unclear, but there's a lot of theoretical frameworks that could potentially explain it, and those are going to be the ones that obviously get a little bit of more work put towards them and have people, sharpen up and clean up that work to try and explain this.
So I guess,
for example, it's always that to and fro, right, between theory and experiment.
So like the anomalous magnetic moment is some diagram that looks like this, and so what you would be looking for is, so here's the muon, the magnetic moment, right? Here's the coupling to the magnetic field at the top, and then the issue is if you include all of the known interactions in the standard model, that's all the stuff that goes into this junk down here.
This bubble g-2.
Yeah, this bubble g-2. And so what it implies is that there's interactions that aren't known about in the standard model.
Yeah.
So there's some other particle. It could be a Lepto Quark.
So your g-2 box, that yellow bubble, is more populated with random stuff than you thought should be possible given the standard model. And that means
which would include a new type of particle that couples to the electromagnetic field, apparently.
Yeah.
If it has to couple to the electromagnetic field, maybe it's coupled to something else. But there's some new particle that goes in this diagram down here at the bottom. Maybe so if it's a new force, then that would imply that there's some other coupling to the muon that goes to this particle. A new force would be pretty gnarly because there's only 4 forces known to nature, and only 3 of them that are known to be quantum in origin.
Yeah, one of them we don't talk about. He's the naughty child. Gravity, we don't talk about.
But so having a new force, that would be pretty cool. Or having a new particle would also be cool, like a particle that has a particularly weak coupling to the electromagnetic field, but it nevertheless contributes to this, and that might give us some indication. Maybe there's a dark matter particle that has a very weak coupling that you can get to in this diagram that then would contribute to the magnetic moment of the muon.
But it's a really good question, right? It sounds like who cares? What why is it important question? This is an indirect measurement, right? It's not telling us exactly why it's different or what's causing it. It's just saying it is. So it's very difficult to explain, and it'll take a lot more work to unravel than, when we found the Higgs, we were like, we already had that tailor-made ready. We know pretty much what this is.
Yeah,
With
no
this, it's a signpost saying, please go look more in this area, rather than a definite, it's A.
Mm-hmm. So when a scientist, like when a particle physicist says new physics, they're talking about like new discovery. And in the case of particle physics, a new discovery is huge. It's more than, I think it's fair to say that the discovery of a new particle, like a new fundamental particle in particle physics, is more than just discovering a new chemical element, right? There are there's 100 and something chemical elements and something like 1,000 different isotopes. This would be like discovering, it'd be like coming home and be like, oh, we found a new family member in our house.
Yeah. Things fall upwards now.
Yeah, this is it's a completely, like a new particle, when you only have 10 particles to work with or 16 particles to work with, it's a much larger contribution or change to things, especially in a situation where we're living today, where 95% of the energy density of the universe, we don't know what it is. And so 95% of the stuff that's out there could be in this anomaly in the g-2.
So it's very, very intriguing. And new physics, people throw around that word, new physics beyond standard model physics. We need it because there's things that the standard model can't explain. You touched on a couple there, dark matter, dark energy, the nature of gravity. We know the standard model isn't the the be all and end all in particle physics. So any signal that we can find that shows us where to go after that model, as successful and brilliant and precise as it's been for so long, is a very, very useful signal. And as I said, it will give us some signposts as to where to go next. That doesn't undermine how important and formative and brilliant the standard model has been. It's just that we know it can't be the final word.
Yeah. So a question came up, and I guess this is probably the op-ed time. Would be what is more important in the long run? I guess so. What's more important, the discovery or the characterization? So you discover new physics, and then without the understanding, or the understanding that comes from later experiments.
I guess it would have to be the understanding, wouldn't it? Just finding something doesn't, have we learned anything new? We just know something is there. Unfortunately, without having that sort of slap in the chops, as you said, to look, this is where you need to look, this is where you need to focus your energies, this is what you need to explain. How do you even do that? It's like telling someone to invent something without telling them what to invent. You need some sort of spur of where to look, some clues as to what your theory should be able to predict. So they both go hand in hand. As I say, there's always that interplay between theory and experiment. So both are important, but I think in the end you want to get to that point, because physics is about explaining why the universe works, of being able to explain, why an experiment has given the value that it has. So the end point is the categorization, I guess.
Yeah, and the same thing kind of has come up in exoplanet science, where 1995 is kind of the breakout year for exoplanet science. There were certainly hints of exoplanets in previous years, but 1995 is the canonical start of the field, like the first discoveries in the field. And for about a decade, probably 15 years, it was all about discoveries. If you discovered a new planet, you were famous. That was what it came down to. Is like the discovery of every new planet was, that was how you made your name.
Because it was novel and something new and something people didn't know was out there, right? So there's always that sort of.
And that's no longer true. It's no longer true that just making a planet discovery is viewed as important as it was back then. And so now it's more like, now that we have these planets, you do the analysis of the population to understand how does that affect our understanding of planet formation. And so, but the Nobel Prize is not given really for the understanding of that comes from it. It comes from, I guess, opening the door or blazing the trail.
Taking the example of exoplanets, I don't think you can underplay, how exciting, particularly in that sort of field in astronomy, where people can. We've both got a friend, Dave Kipping, who does these videos that are very, sort of aspirational and cool music in the background, and it's all the meaning of life and all these sort of deep things. I don't think you can undersell how much just finding those things in that field made people think, I want to be involved, I want to know more. We need to get out there and understand more about where these things are coming from. Potentially they link back to where we came from in terms of life developing. So there's no doubt that they can spur on that understanding. So they're incredibly, incredibly important. There's no doubt about that. We see the buzz about this, on Twitter and it's all over the media, this g-2 results from yesterday. But the end point has to be the categorization. And I guess what you're sort of alluding to is that now in astrophysics, people are saying, hang on, why are those planets that we found like this? How did they develop? How many of this type are there and how many of that type are there? And this type of thing has become more important, that categorization, more than, we found another one to put into the box.
Yeah, there's definitely something to go along with the thing that inspires public interest isn't always the thing that inspires or motivates the scientists. I can assure you that there's at least one person in exoplanets who really doesn't care about alien life. And it's
not Avi, is it?
No, it's me.
Oh, right. I've seen Avi getting some stick over the last few months. I haven't followed it too deeply.
Yeah.
Loeb or Loeb or.
I mean, maybe I shouldn't say this out loud, but like I'm just not interested in the search for alien life. There might be some technical questions that I think would be interesting to see, and I certainly I understand how people can be interested by it. I'm not like I understand that people dig that kind of thing. It's just like I can understand how people like certain types of food.
It's not your cup of tea, as we'd say over here in the UK.
So that's not the thing that motivates me to study exoplanets. So to each their own, which is good. Like you don't want to have everybody studying exactly the same thing, or else you only learn those things. You want to have the variety that's out there. But there are those are the things like discovering planets, and maybe there's life on the planets. These are important questions for other people, and I'm willing to even. I even devote some of my work on, like I've done papers on, or a paper on panspermia. I've done papers on habitability because I recognize that they're important scientifically, even if it's not personally, it's an aspect of my research that isn't the thing that gets me up in the morning, but you still do a good job. Like vacuuming the floor, you do a good job vacuuming the floor, even if it's not like the thing that you enjoy doing the most. So, and discovering life is probably more interesting than vacuuming the floor, to be fair. But so just because though a particular scientific question isn't necessarily the thing that you care the most about, you can still do a good job, and people can, you can still recognize the importance that it has for others.
As my mum says, it takes all sorts, Jason. It takes all sorts.
Yeah.
So if everyone was like you, Sam, the world would be a very boring place, and I agree with that. So,
hey, I really appreciate your time. Is there anything else that you want to say? Do you want to do a shout out for my stream of who you are and where they can find you?
Yeah. So my name's Sam Gregson. I worked on the Lhcb experiment over at CERN. I now have my channel on YouTube, which is Bad Boy of Science. So pop over there. You can find me on Instagram, Twitter, all sorts. But yeah, pop over to YouTube, Bad Boy of Science. You're always welcome, especially if you disagree with me. And, we have Jason over a decent amount, and we're always looking to discuss the next scientific thing that's coming down the track. It's always a pleasure to chat with you, Jason.
Yeah, this has been a good one. So thanks a lot. And I'm Jason Steffen. I go by Horizon Sci on Twitter, which
exactly have a shout out on mine as well, because it cuts both ways.
Yeah, so for better or worse, that's the username that I told. I've been talking with my kids about, choose your username wisely, because it's going to be with you for the rest of your life.
Horizon Sci is pretty good. What's wrong with that?
So it would have been Horizon Science. It was originally going to be Horizon, but then there was a video game that already had that. And so, and then Horizon Science. Anyway,
the European Union funding call is called Horizon, right? And we have a show over here in the UK called Horizon, which is like a BBC science documentary.
Oh, well, definitely. I mean, Horizon's definitely something that, I dig the name, but it's just one of those things. I like the name because, it's an homage to black hole event horizons.
Yeah. And you have a Twitch channel under the same name, right?
Yeah, that's my Twitch channel is Horizon Sci on Twitch, and Horizon Sci on whatever the thing is, Twitter.
Still streaming every Tuesdays and Thursdays. What time?
Yeah, twice a week, Tuesdays and Thursdays at noon Pacific time. Right now, we just finished up about a year of astronomy, and now what I'm doing is going back through. I've made a list off the top of my head of 100 or so, probably not quite 100, but maybe 60 physics experiments, like historical physics experiments. And I'm going through how they were designed, what they ran, what they discovered, like how they ran, what they discovered. And so this kind of fits into that mold as well.
We need to have a look at the old Nobel Prizes that we were going through as well.
Yeah, so we'll definitely need to get back together with less interval between this stream and the next one than there was between this stream and the last one.
We should set up a monthly one at least, and then we can,
that'd be good.
We can do a monthly roundup of the science that's come up that month. Maybe every second second Thursday or whatever of the month or something. I
Yeah.
don't know.
So let's talk and get a schedule set up.
Let's do it. All right, buddy.
Cool.
I'm gonna
All right, hey,
I'm
thanks
gonna
a
go
lot.
get a drink and have a chill out before bed. Have a great afternoon, and let's chat again soon.
All right. Sounds good. We'll talk to you later.
Take care, buddy.
Bye.
Bye.